Hello friends, today we are going to learn the Bell-Colleman cycle. Before going to proceed towards the Bell-Colleman cycle, we will see the little bit history behind the Bell-Colleman cycle. In 1871, the Brighton cycle was developed by the American engineer whose name is George Brighton. This Brighton cycle is also known as Joule cycle. Joule cycle. After that, the Bell-Colleman cycle was developed by the Bell-Colleman and Lightfoot by reversing this Brighton cycle or Joule cycle. The Bell-Colleman was developed by the Bell-Colleman and Lightfoot by reversing the Brighton or Joule cycle. Because of this reason, this Bell-Colleman cycle is also known as reversed Brighton or Joule cycle. Bell-Colleman cycle is also known as reversed Brighton or Joule cycle. After seeing this little bit history, we will proceed towards the working and processes involved in the Bell-Colleman cycle. Now see, this is the schematic diagram of system which works on the Bell-Colleman cycle. This system consists mainly four components. First is compressor, second is cooler, third is expander, and fourth is refrigerator. This Bell-Colleman cycle is followed by the four processes as given. Processes. First process is isentropic compression process. Second process is constant pressure cooling process. Third process is isentropic expansion process. And fourth process is constant pressure expansion process. These four processes can also be plotted on the PV and TS diagram. Let's see how to plot these processes on PV and TS diagram. This is a PV plot of this Bell cycle and this TS plot of this cycle. So let's start. When compressor sucks the cold low temperature low pressure air from the refrigerator and compresses it to the cooler pressure. During this process, the pressure and temperature of the air increases from point 1 to 2 and specific volume of the air decreases from point 1 to 2. So now we will plot this process on the PV and TS diagram similarly. Consider this is the first point, which is entry of the compressor of volume V1 and pressure P1. As air compresses from point 1 to 2, its pressure increases and volume decreases. During this process, the pressure increases from point 1 to 2. The volume of this point, which is outlet of the compressor, at the outlet of the compressor, the volume of the specific air is decreases from V1 to V2, and pressure of the specific air, pressure of the compressed air increases from P1 to P2. Similarly, we will plot this process on the TS plot. This is the first point of the inlet of the compressor. As air starts compressing from 1 to 2, the temperature of the air increases from 1 to 2 but at constant entropy. So let's draw the line vertically upward up to point 2. This is point 2, and entropy of this point is constant, which is S1 is equal to S2. Now the second process is constant pressure cooling process. Constant pressure cooling process means pressure of the air remains constant. When this high pressure compressed air enters to the cooler, the cooling water enters to the cooler from one end and flows over these cooling coils. As water flows over these coils, the air rejects its heat to the water, and this heat gained water out from the other end of the cooler. During this process, pressure remains constant, but temperature and volume of the air decreases from 2 to 3. So we will plot this process on PVTS diagram. As process is constant pressure, so draw this line horizontally leftward, because pressure is constant up to point 3. From point 2 to point 3, this is point 3, pressure of this point, which is equal to P2, P3 is equal to P2, or P2 is equal to P3, and specific volume decreases from point 2 to point 3, which is reduced to from V2 to V3, but pressure remains constant. Similarly, plot this process on the TS diagram. As process is constant pressure, draw the constant pressure line from point 2 to point 3. This is the constant pressure line, P is equal to C. This is up to point 3, the temperature of the pressure decreases. This is the temperature of point 3, T3. This is temperature of point 1, T1. This is temperature of point 2, which is T2. The entropy of this point is also reduced from S2 to S3. So entropy of this point is S3. During this process, heat rejection takes place, and rate of heat rejection can be calculated by using following formula. So let's see what is this formula. First, rate of heat rejection. We can denote, or we will denote the rate of heat rejection by QR. The rate of heat rejection is simply the multiplication of Cp of air and temperature difference of the process, which is from point 2 to point 3. So point 2 temperature is T2 and point 3 temperature is T3. So we can write Cp of air into temperature difference of this process, which is higher temperature minus lower temperature. So we can write T2 minus T3. The expression for rate of heat rejection looks like this, which is QR is equal to Cp of air into temperature difference of the process, which is T2 minus T3. So let's move towards the third process. Third process is isentropic expansion process. Isentropic expansion means the entropy of the process remains constant throughout the process. This process is carried out in the expander from 3 to 4. During this process, no heat is absorbed or rejected by the air. So, as process is isentropic, the entropy of the process is constant, or entropy of the air constant. So, draw the vertically downward line up to point 4 because entropy of the process is constant, which is S3 of 0.4. S3 is equal to, we can write S3 is equal to S4. And similarly, in the PV diagram, we can write, as air expands in the expander, the pressure of the air decreases but volume of the air increases from point 3 to 4. So plot this process on PV diagram. Draw the isentropic line up to point 4. This is point 4. The pressure of this point is decreased from 3 to 4, which is P3 to P4. The specific volume of the air increases from V3 to V4. The pressure is equal to the 0.4 pressure is equal to the 0.1 pressure. So we can write P4 is equal to P1 or P1 is equal to P4. And last process involved in the Bell-Colleman cycle is constant pressure expansion process. This process takes place from point 4 to point 1. During this process, the low pressure expanded air leaves the expander and enters to the refrigerator. When this low pressure cold air enters to the refrigerator, it absorbs the heat of the surrounding of the refrigerator and cools down the space of the refrigerator. During this process, the pressure remains constant, but temperature and volume of the air increases from 4 to 1. So now we will plot this process on the PV and TS diagram. This is a PV plot. As I said, the pressure remains constant from 4 to 1, but specific volume increases from 4 to 1. So draw the horizontally rightward line from point 4 to point 1. During this process, pressure remains constant from point 4 to 1, but specific volume increases from V4 to V1. Similarly, we will plot the TS diagram. During this process, temperature changes, which is increased from T4 to T1, from point 4 to point 1. This is point 1. And entropy changes from S4 to S1. So we will plot the constant pressure line from point 4 to point 1. This is constant pressure line, P is equal to C. And during this process, temperature increased from point 4, the temperature of point 4 is T4, and up to the point 1, the temperature of point 1 is T1. Here, in this last process, constant pressure expansion process, the heat absorption takes place, and the rate of heat absorption can be calculated the following equation by using the following equation. So let's see what is this equation. The heat absorption rate or rate of heat absorption, anything, both of we can say. We will denote the rate of heat absorption by the QA is equal to, it is simply the multiplication of air and temperature difference of the process. The process carried out from point 4 to point 1, and so the temperature of the process is T4 and T1. So this is the QA is equal to Cp into T1 minus T4. Now we will see some advantages, disadvantages and application of the Bell-Colleman cycle. The first advantage of the Bell-Colleman cycle. In the Bell-Colleman cycle, air is used as a refrigerant which is easily available and cheap. There is no cost is applicable on air. Second advantage is since air is non-inflammable, there is no fire risk and hence it is safe in use. Third advantage is air is non-toxic and non-corrosive since it will not hamper our system. Now see the disadvantages of the cycle. First disadvantages of the cycle is low COP, means low coefficient of performance of the cycle or system which works on the Bell-Colleman cycle. Second disadvantage is mass of air required per ton of refrigeration is large, means the quantity of air, mass of air is handled by the compressor is much more per ton of refrigeration. And third disadvantage is size of the system becomes large because the air is compressible. When air is get compressed, its volume decreases, but when air gets expanded, its volume increases, and the refrigeration effect produced by the air is low. Because of these reasons, the size of system increases. Now we will see the applications of the system. Applications. First application of the Bell-Colleman cycle is aeroplanes, planes and jets. In aeroplanes and jets, the Bell-Colleman cycle is used to produce the refrigeration effect. Used to produce the refrigeration effect. And second application is ships. This Bell-Colleman cycle or system which works on the Bell-Colleman cycle used in ships to carry the frozen meats. Used to carry the frozen meat. So friends, we learn about the Bell-Colleman cycle and its advantages, disadvantages and application. In the next video, we will learn about its coefficient of performance, means derivation of its coefficient of performance. So at the last, like the video, share, comment and subscribe.